with circuits, which is just IB stuff. So, hopefully next class I will give you your very own copy of the AP Physics 1 equation sheet. As you may well know, the equation packets that we have been using, these are IB equation packets, and of course you're taking the AP exam Friday, May 16th. So that means that they'll have a slightly different equation list for you. So they're in the copiers. Hopefully I can get them to you next class, if not the class after that. But the equations that we're talking about today are not found in our typical equation sheet, nor are those topics found in the book, which is why I assigned you the different things to read, as well as the videos to watch. So, so we've got a lesson on fluids. Next year, I'll kind of put this more towards the beginning of the year with the forces and stuff, as well as next class will cover the center of mass equations, and that'll wrap it up for the AP information, and then we'll do our circuit chapter to wrap it up. Okay? So, we'll talk about all of the differences and stuff about the AP 1 equation sheet in the future, but I do want to have them on the board so that we can see the equations that we'll talk about today as we discuss more on fluids. So here we go. Let me get my door.
I did not.
So remember, it's been a hot minute since like September.
Density.
So some of these equations you should all already know, like the density equation, the pressure is equal to force divided by the area equation, as well as the buoyancy force equation. We talked about that as well. So the 4 equations that we'll cover today are those two, and then the last two. The last one, of course, is really big, but don't worry, I'll teach you how to do it. Yes. Still got that cough, but hopefully I can make it through our lesson today. Because this is the first day that I've actually been teaching like all day since I got sick 2 weeks ago. So. Okay, so there was, excuse me. So there was one thing that I forgot to put on the things to watch. It was covered if you did the reading, but it wasn't covered if you just did the watching. So I'll do that first, and then I'll fill in with the others. So the first thing is the hydraulic piston example here. So let's say that we have a trapped fluid. It could be water, it could be oil, it could be gas, it doesn't actually matter. But the idea here is that we have two different pistons here. This could be like a hydraulic jack or something like that, where all inside here we have our fluid. And the concept is that in all places in the trapped fluid, the pressure is constant. Okay, so that's the key. So if the pressure is constant, and we know that pressure is equal to force divided by the area here, when we look at our two pistons, so if this is a small piston, it has a certain area 1, and let's say that we exert a force F1 down on that small piston, okay? At the same time, because the fluid is all trapped inside of the device, the pressure is distributed equally all throughout the fluid. So if we've got a force times an area here, we have another piston over here that has a different size, and it's going to give us a different amount of force as well. So knowing that the pressure is constant, that means that I can compare and I can set up not a ratio, a proportion between these two things. So like I can take F1 divided by A1 because that's going to be equal to the same pressure throughout, and that's going to be equal to our F2 over A2. So that's how we would approach a hydraulic piston kind of example, which you may find on one of your quiz questions. So that's how we would do it. Concept is the pressure is constant for a trapped fluid, so therefore the force divided by the area in different parts of the system are going to be equal to each other, and you do the math from there. If the pistons are known to be a cylindrical shape or a circle, then keep in mind that you may need to break down your area in terms of your pi r squared. We're just all coughing.
Oh my God, y'all. Y'all got chill. Y'all got chill.
I promise I'm not contagious. It's just lingering. Okay, so let's move on to the other equations we have here. So we're going to talk about that equation now. So this talks about the pressure, and this relates to like when recall the last time you went swimming in a pool and you like to dive, let's say, down to the bottom. You are definitely aware that as you go deeper and deeper into the water, the pressure is going to increase, okay? And this is a direct result of basically, it's like the water that's above you is pushing down on you, exerting forces acting on you. The further down you go, the more water is on top of you, so there's going to be more pressure that you are feeling, okay? But this doesn't just happen with the water, it happens with all sorts of fluids, so both liquids and gases as well. So if we were to look at this first equation here, so we have our P is equal to P naught plus rho GH. Remember that rho is density, mass divided by the volume as we talked about before. This main P here, this is going to be our absolute pressure, okay? Absolute pressure, or what we feel. The P naught is going to be our atmospheric pressure. Atmospheric pressure. And then our rho GH term, it kind of looks like mgh, which is like the potential energy function. So this is really our depth part of our equation, where our h here is how deep in the fluid we are from the surface. Okay, so we've got our density, we've got our G, we know what G is, and then H is our depth here. As in, if we were at the bottom of the pool, okay, because we dropped something, and so we got to swim down and go get it, okay, so we are at a particular depth H. So again, what we talked about before, the deeper we go, the greater the pressure. Now, if we were at the surface, we would experience an atmospheric pressure P naught, okay? So like, if we're at the surface, if we're not under the water at all, the depth is 0, and so our absolute pressure that we experience is actually equal to the atmospheric pressure, which again, if we think about, well, we don't have any water above us, but we do have air above us. In fact, if we think about it, we are standing at the bottom of a giant air pool. So imagine the atmosphere having a particular depth where we've got the top of the atmosphere goes into space, and then the bottom of the atmosphere, let's say, is at sea level or wherever the land is, okay? And so we're always living at the bottom of the air pool, okay? So knowing that, we are always experiencing the maximum air pressure because we're down at the bottom, Okay. Now, if you go in a plane, or if you go to like the top of a mountain or something like that, where there's a significant change in altitude, there's also a significant change in the air pressure as well. And so that P naught, if we were to calculate this, like here in Jacksonville, it would be a certain number. If we were to go to Denver, which is at a higher altitude than we are, that number would be less. And so we would have to plug in that number as we calculate whatever it is that we need to, okay? But also remember that as we change in altitude, like as we go on a plane trip or as we go to the mountains, the faster the air pressure changes, something happens with our ears, right? Yeah, so if it happens fast, it might be like your ears get clogged or your ears might actually hurt until they pop, okay? We've talked about sound, and sound is a pressure wave, an air pressure wave, and your ears are sound detectors. So there's a little pocket of air inside your ears that allow you to hear the sound through the air. That's why when you go into the water, you can still hear sound, but it sounds really weird because we're used to sound through the air, because there's air on both the outside as well as the inside of the eardrum inside of your ear. So when you go on into a plane or drive up or down mountains, your ears want to pop because there's a difference in the air pressure. Okay, your ears want to equalize with what's on the outside. So if what's on the outside changes drastically, then your body has to adjust. And sometimes it hurts before you actually get it to pop. Oftentimes, like when you chew gum or you swallow or you yawn, the mastibular, I don't know, I'm not a biologist, but the jaw muscles are actually connected to your ears. And so the movement of your jaw helps your ears adjust to the change of the air pressure, which is why that works. So, cool. Okay, so if we were down at the bottom of the pool, then we would experience a pressure P, which is going to be equal to the basically the air on top of us, which is our P naught, plus the water that's on top of us, which is our depth term as well. So this is going to be our absolute pressure. Sometimes we might have like a little gauge, like if you go diving, there's going to be a gauge that tells you how much pressure or how much pressure in the water you're experiencing, okay? And that's actually our next equation, which is really just a special case of this equation. Notice that our P gauge here, okay, P gauge is just this term, our rho GH, which means that this is really just the difference between the absolute pressure and the atmospheric pressure. If we subtract that over, P minus, that's not a minus, P minus P naught, that's really what our gauge pressure is. So the gauge basically takes out the atmospheric pressure and gives you just the pressure due to the water. All right, so we've got our two pressure equations, which are very closely related. Again, the density is going to be the density of the fluid. So if we are in fresh water versus salt water, then that density may be a different number. All right. Any questions so far on our pressure equations? Cool. All right. Next up, we'll talk about the Bernoulli effect, which has a couple of different examples. One, if you've ever seen a convertible on the highway, but with a soft top. Okay, so like the roof is like a fabric roof. It's not like hard plastic or metal. And so you'll see if they're going fast enough that it kind of like poofs out. Okay, so like let's say we've got our car here. Here's our convertible. and typically our roof would look like that. But on the highway, it kind of poofs out a little bit, okay? So the reason here is the fact that fast-moving fluids produce low pressure, okay? So for fluids, if the V increases, then the pressure decreases, okay? So what happens here is as the car is moving at a certain speed V, the air is really moving at that same speed with respect to the car. And so we've got fast air all around the car, okay? So if the air is moving fast all around the car, that means that there's low pressure all around the car, okay? Now inside the car, the air isn't really moving with respect to the car because it's all in the car, okay? We talked about that before. So because the air isn't moving inside, we have a high pressure of air on the inside. And gases, or really all fluids, will want to flow, will want to move from areas of high pressure to areas of low pressure. Like when you watch the Weather Channel and they're talking about, oh, there's a high pressure system in the northwest, and oh, here's a low pressure system coming in to give us some rain and stuff like that. Well, wind is caused by a difference of those two pressures, okay? And wind always flows from areas of high pressure into areas of low pressure. Just like water will always flow downhill from an area where it's higher to an area where it's lower, because that's the natural flow of things, okay? Things don't flow uphill, things flow downhill because of the force of gravity. So the same thing happens with our air pressure as well. So the wind is caused by the air moving from the high pressure system into the low pressure system. And if you think about it, all of our storms are low pressure systems. So whenever you feel the wind blowing in a particular direction, the wind is always blowing into the storm, because the storm is the low pressure system and the wind is coming from an area of high pressure that's somewhere close to it. So as the storm comes close to you, the wind is always blowing towards it as it comes towards you. As the storm moves away from you, the wind still points towards the storm, but now it's blowing in the other direction as the storm passes, which is cool. Okay, so there is a neat little trick that I do occasionally when I go out to a restaurant, and it's not just with my wife, because she's definitely seen this before, but I do this little trick here. And it's really based on, if you've ever seen like a factory with a smokestack, okay? There's a big, tall pipe that extends into the air, okay? So the whole point of this is that the exhaust fumes and the gases that the factory makes inside, they want to get it to the outside, okay? So they make this big smokestack where it reaches fast-moving air. And we know that fast-moving air produces a low pressure, okay? So we've got low pressure, just like our car example. If we've got low pressure at the top of this tube here, and we've got not really moving air inside the factory or the machines that make it, so we've got high pressure. So this naturally, because there's a difference in the pressures, it's going to draw up the air and all of the smoke and stuff. Naturally, it's going to suck it up and out of the factory. So when I go to a restaurant, I kind of do this where I take my straw, but then I take a different straw, okay? Because you need two to make it work right, all right? So what I'm going to do is I'm going to blow across the top of the straw, okay? It helps if your drink is like really full, because there's not a whole lot of air for you to push past and to suck up. The more you drink, the harder it's going to be, okay? But the point here is that as I blow across the top, I'm creating low pressure, and it's gonna suck up the air and the liquid inside of my drink, so that if I'm doing this, you know, to like my kids or friends that don't know what I'm doing, this is what's gonna happen. So I'm gonna blow across the top here, and it sucks it up enough that the actual liquid, the drink, comes spraying out on the people. So, cool stuff. Table tricks that you can show to your friends the next time that you're out. Yes. So I'm blowing across the top, right? So I'm making fast air, and the fast air creates a low pressure right above the straw. And so the faster I do it, the greater or the lower the pressure is. And so there's a difference between the high pressure of inside the tall straw and the low pressure right outside. And the wind, the air gets sucked up, and as the air gets sucked up, the fluid also gets sucked up as well. And then, of course, as you keep on blowing, it gets sucked up, and then you spray your friends. So, cool stuff.
Did you like discover that yourself, or did you like find it online?
Oh gosh, I've known that. I probably learned it in my physics class in high school. So, if not, it was definitely soon after, or maybe like I learned about it just by playing around, and then I learned that, hey, that's actually physics. So I'm not sure which came first. So, but I've known about it for like since I was a kid. So. All right, good. So let's wrap it up with our two last equations here, and these deal with pipes or hoses. Pipes or hoses. All right. So let's say that I want to wash my car. So I'm going to fill up a bucket with some water. So I get my hose, but I happen to have a nozzle that I can attach to my hose. Yeah. So the whole point of a nozzle is basically to change the size or the area, the opening of the hose. Just like if you don't have a nozzle, you put your thumb on the end of the hose and it makes it squirt out faster, right? So the question here is, all right, well, if I want to fill up a bucket, right, because I'm going to wash my car, and so I fill up my bucket with the hose, and I'm like, you know what? I want to fill up my bucket faster. So I put the thumb on the end, and it makes it go faster out of the hose. But as it turns out, the bucket doesn't actually fill up faster because there's this thing called flow rate. And that's what the first equation here, that A1, V1 here. So the A times the V, if we were to look at the hose. So here's a hose with a cross-sectional area A, and the speed of the water that goes through it, V1 here. And then as we reduce the size of the opening at the end here, okay? So I am reducing the size of the tube or the hose. So now we have our A2. So we should be expecting that the water is going to come out faster as I put my thumb on it, right? Okay. Like if I were to be trying to like spray like my kids that are a certain distance away, and I have my hose and it only goes a few feet. If I were to put my thumb on it and put it at that same angle, we've talked about projectile motion before, if I increase the speed, I'm going to increase the range that it goes. So as I put my thumb on it, I find, hey, it does go further because I'm speeding up the water. But the flow rate, this A times V, the flow rate here is actually a constant. That's why I can't speed up how fast I fill up my bucket, because the same amount of gallons per second is going to come out of that hose whether I have my thumb on it or not. Okay, so the flow rate is constant, but the changing of the size of the hose is going to change the speed. So as I reduce the size of the hose, I'm going to increase the speed of the water. So that's where this equation comes from. So A1V1 is equal to A2V2. If we have a certain A times V, that's going to be a constant number. As I reduce the A, the V has to go up because they're inversely related. So that's why when you put a nozzle on your hose, the water speed increases, but the total amount of water that I'm getting per second is still constant. That's what we call our flow rate. So our flow rate has to be constant. That's that A times V. And we see a change in the speed based on the change in the size of the hose. Again, we are assuming that our fluids are ideal. So that means that there's no viscosity, no internal friction when it comes to these particular equations. Okay, so then our last equation comes in when not only we change in size, but maybe also we change in height. As in, it's getting towards summer. Let's say that I want to, get my above ground pool filled with water, right? So I take my hose is attached to the spigot, runs along the ground, and then it goes up. I gotta bring my hose up to a particular height in order to fill my pool, okay? So it may look something like this, where I've got the first part of my hose, and then it's gonna go up a particular height. At the same time, it may reduce in size or change in size, okay? So here, this is the setup for our last equation here, which if you read the section or if you watch the video, both of them give you a good proof of where this equation actually comes from. It really starts from conservation of energy. Now, we don't need to know how to do that big old proof, but if you wanted to see it, then it's there. But I'm not going to do it here unless you really, really want me to later, okay? So here we have, so this is our part one of our hose. This is our part two of our hose. So our part one, we've got the pressure one of the water inside of our hose here, okay? Which is kind of like, so because there's a change in the height, that means that this water is kind of pushing down, causing more pressure on the bottom part of our hose, okay, because of the force of gravity. Okay, so we've got our P1 down there. We have our P2 here. We have our A1 here. We've got our A2 here. We know that based on the size, just like we did here, we have a certain speed V1 here, we have a certain speed V2 here, and then we do have a change in the height. So imagine this is our ground here, so this is going to be our Y1 here and our Y2 here. So let's take a look at our really big equation. So we've got our pressure term, so our P1, okay? So our P1 plus, it almost looks like a gravitational potential energy. Remember PE equals mgh or mgy? So, but instead of the mass, we are using the density equation. Remember, our density is mass divided by volume. And that's part of the proof that we go from this term to here, but we've got our rho g y 1 here. So we've got our pressure term, we've got our potential energy or our height term, and then we have, it almost looks like our kinetic energy equation, 1/2 mv squared, but instead it's going to be 1/2 rho v squared, where again that v is going to be the speed, not volume. So that's a small v here. So we've got our pressure term, we've got our height term, and then we have our speed term. And again, this is all based on conservation of energy, so we can set all three of these things from side 1 equal to all three of these from the side 2. So we've got our pressure 2, we've got our rho g y2, that's going to be based on that height here, and then we have our 1/2 rho v2 squared based on its speed. So this really big equation we are going to use if we have a tube or a hose that both changes size as well as changes height. But we could have some special cases, like let's say we go back to this case where we're not really changing in height. We're changing in the size of the hose, but we're not really changing in the height. So if that's true, if there's no change in the height, so if the change in height is 0, if there's no change in height, that means that both of these y terms go away. Okay, so then my equation reduces to P1 plus 1/2 rho V1 squared is equal to the same thing on the other side. We got our P2 plus our 1/2 rho V2 squared. Okay, now let's say in another case, because when I'm gonna fill up my pool, I really don't need to put on a nozzle, because I know that the faster it comes out, that's not gonna change the flow rate, so why bother with a nozzle? So I'm not gonna change the size, I'm not gonna change the speed, and so if it's just a straight up hose, not changing the size, but maybe changing in the height, because I still have to get up and over the edge of the pool to fill it up, so then I can add this special case. So if the change in the area is 0, okay, that means that there's no change in V as well. There's no change in the speed, and therefore my speed terms go away. My 1/2 rho V squareds go away. So then my equation reduces to this. So we have our P1 plus our initial height term, PGY1 is equal to P2 plus, same thing, rho G Y2. And typically, I mean, we can assume that the Y1, or whichever Y is lower, we can just say that that's 0, and that'll even make our equation even easier, because that term just goes away, because we're assuming our Y1 is 0. Okay, so we have our big old master equation for a hose changing size and changing its height, where we've got all three terms. We have two cases of a special case here, where if there's no change in the height or if there's no change in the size. But all of those are based on the conservation of energy, which is how we get that. But knowing, again, that our flow rate is constant. It doesn't matter how fast the water comes out of it, the number of gallons per second is always going to be the same. Again, assuming we have ideal fluids and the like. In real case, that actually changes, but we're not going to talk about that much. All right, any questions for the good of the order? Yes, Mark.
How'd you get the 1/2 right there?
How to get the 1/2?
Yeah.
Like right here?
Yeah, like on the diagram as well.
On
No,
the
that's
diagram?
Y2. That's Y2.
Oh, it's Y2?
Oh, sorry.
Oh.
Yeah, yeah,
Oh,
yeah.
okay.
That's Y2. That's my
Oh,
bad.
I see. Okay.
Let me write properly.
The-
I saw that too.
All right, guys, I'm gonna give you your 5-minute break. Once we come back, feel free to jump into those pods. Remember the pods, they're not in your regular book. They're in that old IB book link that I posted on the homework schedule. I even gave you the starting page for those pods as well. The quiz is already online as well if you are wanting to do that first, if that's your jam. All right, but feel free to take 5 and let me know if I can be of any more assistance.
Did you not check during spring break?
I took notes.
Excellent. I can check class notes here in just a minuto.
I was so close, I was at 87.
That quiz matter. Quiz didn't affect me. Just do it. I'm working on this quiz.
Did you say garage or lollipop?
The straw. Let me flick in
Yum.
What was your other one? What was your page number?
Might be 1 point.
How we did the bottle thing?
I think the bottle one's
How's the project going in Mr. Rain's class?
That? Oh, I finished it.
You finished it? Already?
Yeah, me and my
It
partner.
was 4.
It was just the PowerPoint.
Ah.
What are you doing?
I'm doing crap. Major depressive disorder.
You,
No, but
took
like, we have
class
PTSD,
notes
but like, what are you doing to like present?
PowerPoint.
Some people are doing poster board, but it's
That's
kind of too much work.
yeah, it is too much work.
Mr. Ray's not even care. He's just gonna give you 100 either way.
So,
Did you see what he did last quarter?